Okay, so what we're going to look at here is some more stuff on motion. You might remember we did this last semester. Um, Obviously, there's some derivative relationships with motion, and it makes sense then that there would be antiderivative relationships. So now that we've got all that behind us, we can go ahead and look at how this works. So what are the basic relationships? We want to start with position, so we know that the derivative of position with respect to time is equal to the velocity with respect to time, and it follows then that we can find the position from the antiderivative of velocity. Okay, and I'm going to put plus c here, even though that would be part of this process, just to emphasize that we have that. The other one we want to look at is that the derivative of velocity is what we call acceleration, and therefore we can say that the velocity is going to be the antiderivative of acceleration. And again, I'll put the plus c there just for emphasis. Okay, so what we've seen here in the previous unit that we've been working on is that when we integrate a rate of change, okay, a derivative, that accumulates the quantity of the function that's changing. Okay, so what does this mean? That means that we can accumulate a change in position by integrating velocity over a time period from t1 to t2. Okay, so this definite integral, the area under this velocity graph, is going to give us the change in the position function, and this is what we call displacement. So we're going to see how we can deal with displacement and actual distance separately in a little bit. So we want to specify that this is displacement, change in position, okay, not the total distance. Change in velocity can be done the same way. We're going to accumulate velocity by integrating acceleration, again over some period of time, t1 to t2. Okay, let's take a look down here. We know how to find average value of a function now, so we can look at things like average position, average velocity, and average acceleration. So in the past, when we did this with derivatives, for example, we said that average velocity was going to be equal to the change in position, okay, over the change in time, which is actually delta S over T2 minus T1. But if you look at this, here we have T2 minus T1 in the denominator, both sides here, and in the numerator, we have the integral of velocity, which we said was going to be delta S, change in S from T1 to T2. So these two things mean the same thing. What's the difference? The difference is if I'm given a position function, I can use this formula to get average velocity, and if I'm given the velocity function itself, I can use this formula to get the average velocity. So the same thing applies with acceleration. You can recall that this was change in velocity over change in time, okay, or change in velocity over T2 minus T1. And so the same thing would apply here, and that's a delta right there, by the way. Okay, next concept here, speed. Remember that speed is the absolute value of velocity. Okay, so speed is the absolute value of velocity. And so all we have to do then is that if we're trying to find the average speed, we're going to find the average value of the speed function. Okay, so here's your absolute value of velocity as a function. Okay, and remember that speed doesn't care about direction, so now is the time to find total distance. So for example, if I drive 30 miles an hour north for an hour and then 20 miles an hour south for an hour, my displacement is going to be 30 minus 20 or 10, but my actual distance covered is going to be the 30 plus the 20 coming back, which is 50. So this will give us the total distance traveled when we integrate speed. Okay, integrate speed. So we integrate speed to get total distance. We integrate velocity to get displacement. So we want to remember that. Okay, so it says here, motion problems are a good place to illustrate the use of an initial condition to find the constant of integration in an antiderivative. So let's start with a simple example. So up till now, we've pretty much just been putting in this plus c and saying that's going to be some constant, could be anything, and it kind of depends on more information. So this is going to be a good place to illustrate what we mean by that and how we would actually calculate that. So suppose an object's velocity is given by v of t equals 4t plus 2, and its position at time 1 is known to be 6. Okay, position at time 1 is known to be 6. So this is the extra information that we need, okay, to actually determine the full function, to find out that value of c. What is the object's position function? So what we're going to do is say, okay, we know that s of t is going to be the antiderivative of velocity, okay, and so let's plug in our formula, 4t plus 2 dt, and that gives us 2t squared plus 2t plus our constant. Okay, now this curve could be anywhere in the xy plane or the ty plane, or whatever you want to call it. It could be anywhere in the plane because of this plus c, could be shifted up or down. If we know one point, okay, if we know one point on this graph, that nails down which particular curve we're looking at. Only one curve can pass through that point. Okay, so we can establish which of the infinite family of vertically shifted curves is the one that we want. So how do we do that? My suggestion is that we just set up, we know what the position function is here. Okay, s of t is this. So let's plug in 1. Okay, that's our t value or x value. Okay, so we're going to get 6 because of this. We know that s1 is equal to 6. So start with the initial condition. And then we're going to say, well, that's going to be 2 times 1 squared plus 2 times 1 plus c. Okay, and that's just this right here. And then we just solve. Okay, so we know that 6 is going to be equal to 2 times 1 squared is 2, plus another 2 is going to be 4, plus c, and therefore c must be 2. And so we know that the full position function is 2t squared plus 2t plus 2 instead of plus c. Okay, so there's our position function. We found that c in this case is 2, and that came from this initial condition. Okay, so that being the case, we can then find the position at any time t. So for example, if t is equal to 10, where is this object located? Well, we plug into 10, so now we know that we have 2 times 10 squared plus 2 times 10 plus 2. This is what we were calling our plus c, and all that works out to 222. Okay? All right. Now, we need an initial condition for every integration that we do. And what this means is that, for example, if we start with acceleration and want to find position, we know that we're going to have to first integrate to get velocity, and so we're going to need a point on the velocity curve, and then we're going to have to integrate again to get the position, and we'll need another point on the position curve. So we need one initial condition for every integration that we do. Okay, so let's start off. We're going to find position here, but first thing we need to do, we're going to start with our acceleration, and we're going to find velocity first. So our velocity is going to be the antiderivative of acceleration. Okay, and our acceleration function is 2t squared dt, and so we integrate that and we get 2/3 t cubed plus our constant. Okay, so let's keep that in mind. And now suppose that we know that v sub 0, put my paper over here, v sub 0 is equal to 1. Okay, so let's go ahead and write v of 0 is equal to 1, and that's going to be equal to 2/3 times t cubed, but we're going to put 0 because that's our t value, plus c. So we know that 1 is equal to 0 plus c, and therefore c must be equal to 1. Okay, so our velocity function should be 2/3 t cubed plus 1. Okay, so this was our plus c from the antiderivative. Okay, so we know that this is our function. Now we're going to find s of t. So we're going to integrate our velocity okay, which is going to be the integral of 2/3 t cubed plus 1 dt. That gives us 1/6 t to the 4th plus t, okay, and now we get another c, another plus c here. All right, and technically we should use a different letter here because we already found out c is equal to 1, but this is okay. All right, so let's plug in our initial condition. We see that we know that the initial position is 3 at time 0, so we're going to say that s of 0 equals 3, and we're going to plug in our s of t function, which is this guy, 1/6 times 0 to the 4th plus 0 plus c. 3 equals 0 plus 0 plus c, and of course that means that c is equal to 3. And so our final s of t function is going to be 1/6 t to the 4th plus t plus 3. Okay, and we can take these two derivatives to verify that. In other words, what we could do is take one derivative, so the 3 goes away, this becomes 2/3 t cubed plus 1, and then we take another derivative, the plus 1 goes away, and we end up with, what is it we end up with? Our original function, right? 2/3 t cubed, no, 2t squared. Okay, you get the idea. All right, so let's do a few examples here to illustrate some different ways that this might come across. Okay, so number 1, we've got s of 0 equals 9, find s of t. So we're starting off knowing a velocity function. We're given this velocity function right here, and we need to find out what is the position function based on this, knowing that the initial position at time 0 is 9. So we'll follow that same process. First thing we're going to do is just integrate the function, sine of t minus t plus 1 dt. That gives us negative cosine of t, okay, minus 1/2 t squared plus t plus c. Okay, so now we're going to plug in 0 for t, and we know that our answer should be 9, okay, from here, and that is going to be equal to negative cosine with t equals 0. So now I'm just using this here. No, minus, not equals. Minus 1/2 0 squared plus 0 plus c. All right, so cosine of 0 is 1. This is negative 1 minus 0 plus 0 plus c. And so 9 is equal to negative 1 plus c. And that means that c is equal to 10. And so s of t, our actual function, will be negative cosine of t minus 1/2 t squared plus t, so that's this here, and then we know that c is equal to 10, so plus 10. Okay, find the displacement, the total distance traveled, the average velocity, average speed, and average acceleration, all of this stuff. All right, so displacement, that's delta s, right? So delta s is going to be just the integral from 0 to 3 over a time interval of the velocity function, which is sine of t minus t plus 1 dt. And we're going to put this into the calculator to do this, to get an actual number. Okay, and I will show you how to do that before too long here. But if we do that, we're going to get 0.490. Okay, remember we want our 3 decimal places, accurate to 3 decimal places, truncated or rounded. Average velocity. Average velocity is going to be, since we're given the velocity function, we're being asked for average, we're going to use our average value of a function formula. So 1 over b minus a times the integral from a to b of sine of t minus t plus 1 dt. Okay, so again, remember that this is velocity right here. And if we do that, we get approximately 0.163. Okay, and it's 1/3 of this. Total distance. Yeah, that's total distance. Excuse me. Total distance is going to be the integral from 0 to 3 of the absolute value sine of t minus t plus 1 absolute value dt. Most of these absolute values of integrals, you're pretty much going to need a calculator unless you have, unless you have a graph in front of you and you know exactly what this thing looks like and can get an exact number. But certainly for this kind of a function, you would need a calculator. So again, I'm going to show you how to do that for too long. And when we do that, we get 2.348. So yeah, I'm using a calculator here and pretty much just plugging in the numbers and getting an answer. The important thing, obviously, is to know how to set up your expression for each thing that you're trying to find. Let's find average speed. Okay, average speed is going to be the same as average velocity. Okay, except we're going to use the absolute value of the velocity function, because this is absolute value of velocity, and that's speed. Okay, so remember, whenever you're talking about total distance or average speed, you need to remember the absolute value. Okay, and then another way that we can find average acceleration is the same way that I mentioned before, where we're going to either use the integral, okay, which is what we did. I guess it was on the previous page. Okay, we can either use the integral or we can use the delta v over delta t. Either way. So notice that we do have the velocity function, so we can find the derivative. But let's go ahead and start with this. Delta v over delta t. Okay, and this is going to be our average acceleration. Okay, so this is our formula, delta v over delta t. So let's plug in here. This is going to be v at time 3 minus v at time 0 divided by 3 minus 0. And that is, let's put this in parentheses, sine of 3 minus 3 plus 1 minus parentheses sine of 0 minus 0 plus 1. All of that divided by 3. And we get approximately negative 0.953. Again, using a calculator to get this. The other way that we can do this is to say, well, acceleration is equal to the derivative of velocity. And if we take the derivative of our function, we're going to get cosine of t minus 1. So we can say that average acceleration is going to be 1 over 3 minus 0 times the integral from 0 to 3 of the acceleration function, which is cosine of t minus 1 dt. And again, put that in the calculator, we get minus 0.953. So we get the same answer doing this two different ways. It depends on what we're given. Okay, if we're given the velocity function, okay, we can do the delta v over delta t thing. If we're given the acceleration function, we can use the formula here for the average value to get that.